Welcome, everybody. This is the June MagLab, MagX. And I just want to announce that we will have a MagX on July 25th, and that will be David Labalestier and Lance Cooley talking about fusion. But right now, I'm really delighted that we have our own director giving the MagX talk today, and our discussion leader is Dragana Popovic. And Dragana, why don't you take over from here?
Thank you, Laura. It is my great pleasure to introduce our today's speaker, Greg Boebinger, who does not really need an introduction because he has been the lab's director since 2004. Nevertheless, I would like to remind you that Greg is a highly accomplished condensed matter physicist. He obtained his PhD at MIT in 1986, where he used high magnetic fields to study the fractional quantum Hall effect. Following a brief postdoctoral fellowship in Paris, he joined the research staff at Bell Laboratories, where he established a unique pulsed magnetic field facility to study properties of various types of materials. This is also where he started his research on high-temperature superconductivity, for which he is best known. In 1998, Greg moved to Los Alamos to become the director of the Pulsed Magnetic Field Facility at the then new National High Magnetic Field Lab. And in 2004, he moved to Tallahassee to become the director of the entire lab. And he joined the faculty in the physics departments at both FSU and the University of Florida. Greg's research accomplishments in high-temperature superconductivity have been recognized by various honors and awards. For example, he's a fellow of the American Physical Society, a fellow of the American Association for the Advancement of Science, a member of the American Academy of Arts and Sciences, and a member of the US National Academy of Sciences. So without further ado, I would like to give the Zoom to Greg, but let me just remind everyone to make sure they're on mute during Greg's talk, and please hold your questions to the end.
All right, thank you very much, Dragana. I see we're out of time. I appreciate all those kind words, and it was a great honor to be asked to give one of the 6 science talks from members of my admission class at the National Academy of Sciences. And it was a 15-minute talk that I gave in April. And I'll be giving this talk almost as if you're the same audience. You can, and part of the reason is I want you to see how I represent the lab when I'm out discussing what it is that the lab does. So I've kept all the same slides. I've inserted maybe 4 slides that have a big garnet and gold star on them because I've got a little bit more time here today. And there's I've reinserted the last message that I really like to deliver, but I didn't have time and took it out of my National Academy talk. So my talk is on materials, energy, environment, and life, research at the National High Magnetic Field Laboratory. We've been asked to give a brief biographical note, and I got into high magnetic field research through this gentleman, Peter Wolf, who is director of the Francis Bitter Magnet Lab at MIT from 1981 to 1987. He recruited me in 1981 to be an MIT graduate student, and he plugged me into research at the Magnet Lab. And not just any research, but the research of Horst Stormer from Bell Labs and Dan Suey from Princeton, who were visiting users of the Francis Bitter Magnet Lab. They, just before I joined the group, had discovered in 1982 the fractional quantum Hall effect. And in 1998, they were awarded the Nobel Prize in Physics for that discovery. And from Horst and Dan, I learned 2 important messages, 2 important lessons about research. From Horst, I learned that when the experiment isn't working, go get some coffee and keep on working. And from Dan, I learned, go get some sleep and come back fresh tomorrow. So I knew, depending on the answer I wanted to get, who to ask for advice. This photo of the 5 of us, we are the research group, and we're celebrating in February of 1984 the achievement of ultra-low temperatures at the time and ultra-high fields for that time to do early research on the fractional quantum Hall effect, which required high-quality 2-dimensional metallic samples and extremely low temperatures and extremely high magnetic fields. Now, since then, it's become much easier to observe the fractional quantum Hall effect, and much to my surprise, it's now being explored as a strategy to realize a quantum computer. But the backstory to this photograph is that this was taken immediately after I had completed the MIT graduate student comprehensive exams. And I was pretty sure that I had flunked them. And so I was equally convinced that one day the caption of this photo would read, front row, Horst Stormer, Dan Suey, back row, Al Chang, Peter Berglund, unknown former student. Al Chang was a postdoc in the group. He's now at Duke University, and Peter Berglund just retired from Aalto University in Helsinki, Finland. Now, the Magnet Lab designs and builds magnets that are 5,000 to 2 million times more powerful than the Earth's magnetic field. It provides access for 2,000 researchers annually to use these unique magnets. And this talk is designed to answer the question, why would anyone want to do such a thing? Well, the MagLab is a 3-site partnership among Florida State University, University of Florida, and Los Alamos National Laboratory. It's the only facility of its kind in the United States, and it's the largest and highest powered magnet laboratory in the world. We're funded primarily by the National Science Foundation and also receive considerable funding from the state of Florida and Department of Energy. So how strong are the MagLab's magnets? And before I get into that, let me just remind you, if you have a circulating electrical current, you get a focusing of the magnetic field in the center of that loop of electrical current. And so we build electromagnets essentially following this architecture. And if I choose a few examples of magnetic fields in a solar system or city near you, the Earth's magnetic field is a measly 50 microtesla. They're plotted over here in this very helpful graph. The sun is not much stronger unless you're at a sunspot. Junkyard electromagnets that can pick up cars and are made of copper wire and iron oxide magnets get 1 entire Tesla. And hospital MRI superconducting magnets are at 1.5 to 3 Teslas. And the magical thing about superconducting magnets is that the wire is made out of a material that can conduct electricity without any friction whatsoever. So if you start an electrical current going in a loop of superconductor, as long as you keep it cold, that current will circulate for longer than the age of the universe. There really is no friction whatsoever. So if I add the Magnet Lab's magnets, or at least a few of them, to this graph, here you can see we have, these are 4 of our world record holding magnets. We have the strongest MRI magnet in the world at 21 Tesla for research on mice and rats. We have the strongest superconducting magnet at 32 Tesla, the strongest continuous field magnet at 45 Tesla that combines superconducting and resistive elements. And this is 1,000,000 times the Earth's magnetic field. If you want to go higher than that, you need to turn the magnet on and off in less than a second so that the magnet doesn't melt due to the heating from the electrical current. And then you can achieve 100.7 Tesla, which is the strongest magnetic field ever generated without blowing something up. So this is a picture of the world's most powerful continuous field magnet. If you'd like to see more of it and learn about this magnet, there's a Veritasium video on YouTube. Just go to YouTube, search for World's Strongest Magnet. It has over 9 million views, and it's only been up for a couple of months. I just ask that you not do that for the next 12.5 minutes. This is a photo of the magnet. You really can't see much of the magnet. This is the bottom third of the container that holds the magnet. And I guess, can you see my cursor, or should I turn on the pointer?
I can see it.
Yeah, I can see it.
Okay. And so this 45 Tesla magnet is 10 meters tall, 30 feet tall. It has 5 tons of superconducting magnet in this cylinder, which extends above into the next floor of the building. And that magnet is surrounding 2 tons of a resistive magnet, which in turn requires 30 megawatts of electrical power and 8,000 liters per minute of cooling water. So we can run this magnet theoretically forever, as long as we can afford the roughly $3,000 per hour electrical bill. The MagLab attracts researchers from around the world. This is our Delta Airlines map. Researchers depicted by a purple line have come from their home institutions to our facilities in Tallahassee. The blue lines are folks who've gone to Gainesville, and the red lines are those that have gone to Los Alamos. And in 2021, which was a pandemic year, we hosted experiments by more than 1,600 users from 160 institutions across the United States and from a total of 279 institutions throughout the world. And there are national magnet labs in Europe, in Japan, in China, and sometimes researchers in the vicinity of those labs come to our lab either for unique magnets or unique techniques, or more often for the unique expertise that we have among our scientific community at the MagLab. In 2021, the MagLab helped to train 2,035 postdocs and over 500 graduate students. So education is a major part of our mission. And users published 400 refereed papers, including 6 papers in the greatest scientific journal in the world. That got a big reaction. 4 major MagLab research themes that I'll touch on. I'll spend most of my time on materials. I'm a condensed matter physicist. And for this talk, this is where I've added the extra material from the National Academy talk. Energy, environment, and life. Many of the world's scientific challenges are just too big and too broad for one scientific discipline to solve. The MagLab brings together scientists from many disciplines, from physics to engineering, to chemistry, to biology, to biomedicine, who address these challenges with the help of the world's highest magnetic fields, using techniques that I'll be touching on for the rest of my talk. Now, not all materials are found. In fact, since 3000 BC, most materials are invented. And perhaps the last person to have only used found materials is the Iceman, found in the Alps. He came from 3000 BC, 5,000 years ago, and he relied entirely on found materials, clothing from animal skins. He had a stone dagger, he had a copper-bladed axe, and you can find almost pure copper in nature. One of the earliest invented materials is bronze. It's a mixture of 90% copper and 10% tin. And it really was an invention to create this new material that was better than stone or copper for both tools and weapons. And it created the Bronze Age. Now, this star indicates this is a slide I did not give at the National Academy talk. Bronze, steel, and silicon all illustrate that usefulness motivates the invention of many new materials. But so does aesthetics. Here's an example from the Han Dynasty, where the terracotta army was brightly colored originally, and most of these colors occur naturally in nature, except for the blue and the purple. And these are human-made pigments that required very high temperatures and very good temperature control, and we're still not certain how they developed this technology. They need a flux in the modern terminology. We're sure they didn't understand the chemistry at that level, but they were able to figure out a way to make Han purple and Han blue. They lost the technology. I'm convinced at some point, one postdoc forgot to tell some key step to the next postdoc, and the professor hadn't been in the foundry for a decade. And so they lost the ability to make these materials whose fabrication was a state secret. So the Qin dynasty, which gave the name China to the country, made the terracotta warriors using the first synthetic purple pigment. This is the second blue synthetic pigment. The Egyptians had Egyptian blue. And they did it to protect the emperor in the afterlife instead of sacrificing real warriors. So these people needed to look realistic, or they would have killed actual warriors. And so material science is one of the few sciences that can make a claim to saving lives for more than 2,000 years. Jumping ahead 5,000 years, high-temperature superconductivity was discovered in 1986, and it's still not understood. And the reason we call these high-temperature superconductors is that when we make a coil into which we put an electrical current out of these materials, they superconduct with no friction at about 100 Kelvin, whereas previous superconductors only went up to about 10 Kelvin. And room temperature is 300 Kelvin. So this leap was a huge step towards room temperature superconductivity. Now, the first class of these high temperature superconductors to be found had something in common. And they had a two-dimensional square lattice of copper atoms, and each copper atom had one electron sitting on it. And if you invented a technique to remove 6% of the electrons, then superconductivity emerged. for reasons we don't yet understand. And if you remove 17% of the electrons in any of a dozen of these different compounds, it optimizes high temperature superconductivity. So there's a common behavior that we still don't understand about this high temperature superconductivity. And we can create a phase diagram of temperature versus hole doping, which is just a fancy term for how many electrons are we removing because it leaves behind a hole. So as you get to 6% holes, you get the superconducting phase. It's optimized at 17%. And these three phases that are in red, we understand. The two in black, we're still trying to figure out. But you've got a dome of high temperature superconductivity that's between an insulating magnet and a non-magnetic metal. And we've since found dozens of different classes of material that share this common phase diagram. And we don't understand why that phase diagram is common among so many different superconducting materials. So from my perspective, as someone who does research using high magnetic fields, I wanted to use the high magnetic fields to determine what's under the high temperature superconducting dome. So it was exciting initially that these things superconduct up to 100 Kelvin, but now that's an annoyance. I want to peel back this superconductivity to see what's happening underneath, what's giving rise to the superconductivity. So over here, we've plotted in low magnetic fields, what are the number of mobile holes per copper as you increase this hole doping? And as you might expect, as you increase the number of holes, in other words, remove more and more electrons as you move this way, then you're getting more and more mobile holes, mobile charge carriers. But you can't tell what's happening at low temperatures because the darn superconducting phase gets in the way. So with a magnetic field of 60 Teslas, you can remove that superconducting dome and see that underneath you get this peak in the number of mobile carriers that occurs right at the same 0.17 doping where superconductivity is optimized. So you get the ability to see what's happening at low temperatures. And this is evidence of a phase transition at absolute zero temperature that seems to somehow create or stabilize high temperature superconductivity. It occurs at the same doping where in the resistive state, where the material is the best at being a superconductor. So either nature is telling us that these two things are linked, or nature is being incredibly cruel and misleading us. Well, the physicists still don't understand high temperature superconductivity, but the engineers are not waiting around for the physicists. And so in 2017, the MagLab used high temperature superconductors to build a world record 32 Tesla all superconducting magnet for our user program. This is the high temperature superconducting inner coil that will then go inside this, or was then inserted inside this outer coil made of conventional superconductors for this total 32 Tesla magnetic field. And this photo here on the right is just an enlargement of that high TC coil. And at least partially because of the success at the Magnet Lab, there's now $5 billion of venture capital that's invested in magnets made from high temperature superconductors in an effort to realize economical nuclear fusion. So why study new materials? And here's a few of the new slides. Well, it's because for electrons, every material is a new universe. My high energy physicists and my astrophysics friends only get to study one universe, but we get to study hundreds. So if a single layer of electrons on a square lattice of copper atoms surprises us by creating high temperature superconductivity, what surprises are in store when you find a material that has a double layer of electrons on a square lattice of copper atoms? This is a different universe as far as the electrons are concerned than this one. Well, it turns out that Han purple is such a material with a double layer of electrons on a square lattice of copper atoms. And so, in modern terminology, Han purple is a quasi-two-dimensional magnetic insulator with a gap spin dimer ground state. And we're pretty sure that they didn't know that in the Qin dynasty. And what happens is that the electrons on each barbell, one in the lower layer and the one right above it in the upper layer, they pair up and they behave like completely different particles. Electrons are fermions. Each one has 1/2 spin, which is the smallest unit of magnetic field you can have. These electrons pair up and they save magnetic energy by anti-aligning their spins. and then they act like a single particle. And so now the total spin is 1 or 0. But in either case, particles with 0 and 1 spin are bosons, and whereas fermions try to stay away from each other because they have to be in different states, bosons like to be in the same state. And in fact, lasers are an example of this boson behavior where the photon particles like to all go into the same state. So in this material at 0 magnetic field or low magnetic fields, we have the original state where the pairs of electrons have their fields anti-aligned. But if you get to a high enough magnetic field, you start to align the spins until finally above 50 Tesla, all the spins are aligned. So these are called triplons for technical reasons I won't go into. And the magnetization goes up. It's measuring the number of triplons you have. So the magnetic field tunes the number of triplons. And over this range from 23 to 49 Tesla, the triplons, which are bosons, do something which electrons don't do. They undergo Bose-Einstein condensation, much like photons all falling into the same state to become a laser beam. In this case, for those of you who are in physics, you'll know that if you measure something called specific heat and you see a signature like this, the lambda transition, this looks like the Greek letter lambda, this is a smoking gun that Bose-Einstein condensation is taking place in this double-layered material. So this is proof that these electrons have forgotten that they're fermions, they've paired up, and they've become bosons in this material. And this same transition is seen in superfluid helium, for those who might be interested in that. So we've got a material where the electrons are behaving very differently. In a single layer, you get high-temperature superconductivity. In a double layer, you get Bose-Einstein condensation. So now let's move to energy. The MagLab's ion cyclotron resonance magnets can weigh individual molecules in complex fluids. So what we do is we spray a single drop of petroleum, say, into the magnet, and the molecules ionize. And then each molecule undergoes an orbit inside this magnetic field, much like planets around the sun, but in this case, instead of gravity, it's the magnetic field that's causing this motion. And you measure the frequency of that cyclical orbit. And the heavy molecules move slowly, the light molecules move rapidly. In fact, the frequency of the orbit is inversely proportional to the mass. And because you can measure time very accurately, you can measure the mass very precisely. And the MagLab can weigh molecules to identify more than 100,000 compounds in a single drop of oil. So if I were to zoom in on this figure, I would actually have not just what are shown on this screen, but 100,000 different spikes. And each spike can be identified with a specific chemical formula from a specific molecule. And if you
maybe if you can summarize quickly, we are running out of time. It would be nice to have some time for questions.
Okay. If you know every chemical in petroleum, you can refine lower grade crude, determine what's clogging pipelines, and analyze oil spills. We can also analyze batteries, where we can tell where the lithium is moving throughout a battery by using the MagLab's, I somehow lost track of time, nuclear magnetic resonance magnets. We can tell that the lithium is going through the ceramic in this new battery architecture that uses solid electrolytes rather than the liquid ones that tend to catch fire. We're analyzing what comes out of permafrost when it melts by monitoring the 6 major rivers that drain into the Arctic Ocean. We can make magnetic resonance imaging go high definition to see organs in ultra-sharp focus and to track how water diffuses along nerve fiber bundles. We can image individual cells, in fact, not just organs. And so my final example is that MagLab Research is not just hydrogen MRI, it's also sodium MRI. And this is a state-of-the-art MRI image. The high magnetic field allows us to not just image the hydrogen that's in water, but it images sodium. Now, why would we put up with such a blurry image? It's because dying cells absorb sodium. And even though we don't know why, we can use that fact. This is a tumor in the mouse brain. So we give the mouse a taste of a candidate chemotherapy that's too small to damage its immune system. 4 days later, if the tumor lights up, we know that these tumor cells will die in response to a heavier dose of that chemotherapy. So we know that this chemotherapy treatment is the correct treatment to kill this specific tumor, and we've not damaged the mouse's immune system. So user research at the MagLab advances our knowledge about materials, energy, the environment, and life. New materials with new capabilities need to be invented. My thanks to the 500 scientists, engineers, and technicians, administrators, and staff who did not find the Magnet Lab, they invented it. Thank you very much.
Thank you, Greg, for such an excellent presentation of the Magnet Lab to the Academy and to us. So we have some time for a few questions. If anyone has a question, will you please raise your hand? You can ask questions about science or the Magnet Lab.
It's a good place to work.
Yes. Well, while we are waiting, maybe I can ask a quick question. I mean, some of the research that traditionally required highest available magnetic fields can now be performed at lower fields due to the improvements in sample quality or discovery of new materials. So, and I think we are all at the DC field facilities seeing a reduced demand or reduced activity in those so-called traditional areas of research. At the same time, condensed matter physics community is moving, shifting towards research related to quantum information science that may not require high magnetic fields. So I'm curious, in your opinion, what does the Magnet Lab need to do, if anything, to remain relevant for user research in this new scientific landscape? Right.
So whereas I share your worries, I have absolutely no concerns because I've seen enough things come around the corner that are unexpected, that drive new frontiers that require high magnetic fields, that I have a faith that it continues. And in fact, we've had to split quantum materials research from one science driver into three just to start capturing. Some of it emphasizes more correlated electrons. Some of it emphasizes atomically thin materials and the new physics that comes out of those. And I forget even what our third one was right now. So you're right, fractional quantum Hall effect, you can do a lot of those experiments at lower fields, but it needed to be discovered at high fields. The high temperature superconductors, some people are studying dirty samples so that lower fields can suppress superconductivity, but fundamentally, maybe the cleaner samples are the ones that will finally untease the mystery. So I remain completely confident. We find more and more experiments that require high magnetic fields. The user program keeps growing. And it's only if you look at a single field that the number of users drops off when it becomes possible to do the techniques at lower fields. New things fall in place.
Thank you, Greg. Ryan has a question. Ryan?
Yeah, thanks. So I really like the story about the cuprates and then what's it called? The Han purple.
Yes.
But part of the story of the cuprates is designing, the doping series, changing the number of electrons. What happens in the Han purple when you change the number of electrons?
So this is actually an insulator.
Okay.
And so the electrons don't move, but the triplons move, because you can have one triplon, say, here in the corner, and the rest are all singlets. And then all you have to do is flip two neighboring spins, and suddenly the triplon has moved the next space over. So I'm not aware of any exciting result that comes out of trying to change the doping. I don't know that it can be controlled as easily as it can in the cuprates, either by doping with strontium or playing with the oxygen concentration. I'm not sure that I know of anyone who's been able to fabricate samples with different dopings. But there are dozens of these compounds, and they show Bose-Einstein condensation in temperatures exceeding 10 Kelvin. And in one case, there's a material where they haven't even gone up to high enough temperatures to see where the Bose-Einstein condensation goes away, but the evidence isn't quite as strong that that is, in fact, a material that's in this class of materials.
That's interesting. Thank you.
Yeah, I think maybe there is time for a very quick question, if anyone has any.
Dimitri.
This is the time. Dimitri, go ahead.
You're muted.
Yeah. Yes, thank you, Greg, for yet another energizing, nice talk, which portrays truly spotless, brilliant trajectory of the MagLab. But still, I would like to ask you if you think there were any strategic mistakes that happened in the MagLab over your tenure here. Not the small ones, but something that you would like to correct.
What are you getting at, Dimitri? Is there something you know that I don't?
I just wondering.
So I'm not aware of any. I certainly can talk about misconceptions I had. I was convinced that when the 60 Tesla controlled waveform magnet came online, that would be the end of capacitor-driven magnets. But it turns out that, in fact, those controlled waveform magnets and the generator-driven magnets are sufficiently expensive that you don't want to use them routinely. And you want to have capacitor-driven magnets in order to do the dozens of pulses. So we get a lot of credit from the user community that they're comfortable assigning a grad student to a pulsed magnet thesis because they know they'll get the dozens or hundreds of pulses they need to tell a complete story. And that would not come out of the generator-driven magnet. So I mispredicted the death of capacitor-driven magnets once this new technology came on board. They're actually complementary. I've been really impressed that the DC magnets, we've stayed ahead of the curve because when we replace aging infrastructure, which is an ongoing challenge, particularly these days, since everything's that we haven't replaced yet is about 30 years old. But when we do the replacements, we're also doing upgrades. And so we've continued to stay ahead of the curve. When we were gathering, we were talking about the Project 11 magnet. That was only possible because when we were upgrading our power supplies, we were also increasing their power ratings so that we could drive bigger and more powerful magnets. So I'm sorry, I'm not aware of any crises.
Thank you so much, Greg. I'm afraid that we are totally out of time, so I will give this back to Laura.
Thank you very much.
Thank you very much.
You.
This will be posted in a couple of days, and this was terrific. Thank you, Dragana and Greg.